All right, good morning, everyone. So let's remember what we were doing last time. We were looking at the least squares solution in a different way. The first time we derived the least squares solution looked like this. And this is a very common way that you see least squares solutions described in general. In order to do it this way, what we did is we took all our features, we put them in a matrix, but then we also added a column of ones to create this augmented feature matrix A, and then that was used to come up with this expression. And while the expression is nice and concise, one of the things that it's lacking is an interpretation. It's difficult to see exactly how the statistics of the data affect the least squares solution. So what we did next is we said, can we re-express it or rederive it in terms of some of the sample statistics? And in particular, we were looking at things like the sample mean of the feature vectors, the sample mean of the targets, the sample autocovariance matrix of the feature vectors, and the cross covariance between the feature vectors and the targets. And these latter quantities are just vector valued extensions of the scalar valued quantities that we defined and worked with in the first unit. So we went through the derivation and we got an expression here for beta naught. So that's the very first coefficient in the beta's vector, the intercept coefficient. We have an expression for that depends on the remaining beta coefficients. And then we have another expression over here for the remaining beta coefficients in terms of this autocovariance matrix and cross covariance vector. So putting this all together, we can say that the least squares vector looks like this. There's the first element, then there's the rest of the elements. The first element has this form, that's just a scalar, and the rest of the elements have this form, and that's a vector. So now that we've expressed it this way, you can see exactly how things like the mean and variance of the features and the targets and so on, how they affect the least squares solution. So this is a much more intuitive way of describing it, but of course it's mathematically the same as the other expression, it's just written in a different way. So let's compare it now to what we did in the first unit on simple linear regression. So in that case, the difference was the feature vector that we have now was just scalar, xi. That means the sample mean of the features was also a scalar. The autocovariance matrix of the features was just a scalar, and in particular it's the variance. And then the cross covariance vector was just this cross covariance scalar. So, and what we derived in the last unit was we had the expressions beta naught was y bar minus x bar s xy divided by s xx. And for beta 1, it was s xy divided by s xx. And if you compare these, you can see that they line up. So here we're dividing by SXX. Here we're inverting this matrix. So we can't, when we invert matrices, we have to be very careful about on which side the inverse exists. So I cannot take this matrix inverse and move it to the other side, right? The dimensions wouldn't even work. But with a scalar, I could do 1 over Sx on this side, or I could do it on this side, it doesn't matter. So the expressions might look a tiny bit different, but really they are equivalent. Okay, so it's nice to see everything matches up. Any questions on this part? This is finishing up our re-derivation of the least squares solution. Okay, so now let's briefly talk about how we implement these things in Python. And we'll see there's actually many different ways to do it. So one thing that's done in the demo that I'll just point out right now is that the entire data set, which has 442 samples, is actually split into two subsets. The first we call the training data, and this subset is what we use to compute those beta coefficients. And then we hold out some 142 remaining samples, and we use those as a test to see how well our predictions are. Because we can take the beta coefficients that we learned from the training data, and then we can apply it to the features from the test data. We can then predict the test targets and see how well we've done just as a check. So this idea of splitting the data into two different subsets, we call it train test splits. This is actually going to be one of the major themes of the next unit. So it's not a major theme now, but it's just something that's done in the demo. Okay, so discussing now how can we compute the least square solution. So I'll show you several approaches. So one approach is to use this first expression that we derived. So to do this, we first have to make the A matrix, and then once we have the A matrix, we can put it into this expression. So how do we make that A matrix? Well, we can make this ones vector here using the numpy.ones. We just have to tell it the dimensions, and it makes a vector of all ones. And then we've already made this is the training features. We've already made that matrix, and we can then use this H stack, horizontal stack, to stack the ones next to the X matrix like this. Now that we have our A matrix, we could, number one, we could do a matrix multiply, a matrix inverse, another matrix multiply, and so on. But it turns out that that's not the most efficient method. If you want to explicitly compute this matrix inverse, this grows, the complexity is cubic in the dimension of the matrix. And if you instead use a efficient linear algebra routine, something that's in this LAPACK library, to directly solve the least squares problem, you can actually do this with a complexity that grows with the square rather than the cube. So that's what's done here. This is the NumPy linear algebra library, the least squares. You just tell it the matrix A, the target vector Y, and it computes a couple things, the first of which is the beta vector. So this is going to be a more efficient approach than this one, just computationally, but it should give you the same solution to numerical precision. Okay. All right. Any questions on this? Okay, so this is not the only way to do it. In fact, the way that I'm going to recommend and the way that we're going to use for most of the remainder of the term is to use some of the routines in this Scikit-Learn package. So Scikit-Learn, again, that's like the machine learning package for Python. And the way that you do it here, and what's nice about this framework is we'll see this framework that we're using for linear regression, actually the same framework, the same interface is used for many other types of regression that we'll see later. So what you do is the first step is you instantiate this linear regression object. This sort of sets everything up. The next step is you give that object the data, your X and Y training, and you tell it to fit the coefficients to the data. And what it does is it essentially solves this internally, and it stores the beta coefficient internally within that regression object. So it's not reporting it to you unless you ask for it. It's stored internally. Now that the coefficients are in there, if you want to make some predictions of the targets from new features, you say regression.predict, and now it will report for you the predicted test targets because we're giving it test features. So finally, we can take those test target predictions. We can look at the difference between the test and the true, square it, and take the mean. If we would have actually summed it rather than taking the mean, that would have been the RSS. But right now we're taking the mean, so I'm going to call this a normalized RSS. It's just normalized by the number of samples. And using this normalized RSS, we can compute the R squared, which, if you remember, that's the metric by which we judge linear regression. If R squared is 1, that means it's perfect. If R squared is 0, that means it's trivial. And if R squared is less than 0, it means it's worse than trivial. So in this case, on the test data, we got an R squared of about 0.51, which is somewhere between 0 and 1, so definitely it's not perfect, but it's not terrible. It's just what you get for this data set. So this method is, linear regression is going to be kind of the preferred method, and we're going to use this over and over again through the term. So you instantiate, you fit, and you predict. Those are the main 3 commands. Okay. Any questions on the implementation issues? All right. So let's talk briefly about comparing simple linear regression to multiple linear regression. So remember, the difference is that in simple linear regression, you have one feature, one predictor, whereas in multiple linear regression, you have multiple features and predictors. So these are really the differences here. So the question is, what's the benefit of using multiple linear regression over simple linear regression? Let's just do a little experiment. This is done in a demo. So what we're going to do is, this particular data set has 10 different features. But what we could do is we could use them one at a time to predict the targets. So we only use the first feature, predict the target, only use the second one, predict the target, and so on. And each time we do this, you can see what's done here. You compute the mean of the feature, you compute the cross covariance between the feature and the targets, compute the variance of that feature, then you can compute beta 1, compute beta 0 by the equations we derived. Finally, you can compute the R squared coefficient and print it out. And this is in a for loop where you go over all the different features. And so you can see here for the different feature indices, J goes from 0 through 9. You can see the R squared that was achieved, as well as the coefficients themselves. So when we look at the R squared here, we see that in general, the values are not very high. Sometimes they're very low. Look at this one. This is 0.001. This is close to doing nothing. And then the best we get is actually this one, 0.34. Now, if we remember with multiple linear regression, we got 0.51. So you can see that there's definitely a gain to using multiple features to predict rather than a single one. And what you can say in general is that least squares linear regression, let's say multiple, least squares multiple linear regression performs at least as well as least squares simple regression. And I'm going to write here on the training data. As we'll see a little bit later, this may not hold true on the test data. So it could actually be that on the test data, you're better off using a subset of your features, not all the features. We'll understand more about that in the next couple units. But for now, if we just focus on the training data alone, and we're saying which method works best, if you measure your performance on the training data, then definitely multiple linear regression is as good and usually better than simple linear regression. Okay. All right. Any questions on that, or any questions on anything so far? Okay. So let's talk now about feature transformations. So we saw already in the last unit that linear regression can get more powerful if you transform the data before you apply linear regression. And one of the most important kind of transformations we need to deal with is when we have categorical data. What's meant by categorical data is data that is not ordinal, data that is in the form of categories and not ordered numbers. So, for example, if we want to predict the miles per gallon of a car, let's call that Y, given the horsepower X and the brand of the car X2, where the brands are Ford, Honda, and BMW, we encounter a categorical variable. There's no clear ordering between Ford, Honda, and BMW. Those are just different brands, different categories. On the other hand, if I think about the horsepower, there's a very clear ordering of real numbers, from negative to 0 to positive. So numbers like 1, 2, 3, those are ordinal. There's a clear order to them. Categories like this have no clear order. They're just 3 different things. Cats, dogs, cows, whatever. So in order to handle this case, when we have these categorical features, the main approach people use is called one-hot coding. And what you do is you code these categories, or brands in this case, as binary vectors. So let me show you exactly what we mean. So again, the example we have at hand is that the brand is either Ford, Honda, and BMW. And we previously thought about this as a variable x2. We're actually going to expand x2 into 3 new variables, and we're going to assign that vector of 3 variables either 1, 0, 0, 0, 1, 0, or 0, 0, 1. So this is called one-hot coding because this vector is one hot. There's only one non-zero in the vector, and what you're doing is you're just shifting the position of that non-zero. This gives you a way to represent these 3 categories without making any explicit ordering among them, and that's what we need to do. So let's say that I do this. I have my Y as my target. Horsepower is ordinal, so I don't need to do anything differently than what we've already learned. Now my brand X2, I've split that into 3. My new model looks like this. So, and again, these are the 3 options we have. So as you can see, we now have 3 different new predictors, beta 2, beta 3, and beta 4, and they multiply these new expanded features that we created with one-hot coding. Okay, so that's the idea. Before I give you the interpretation, I want to make sure this is clear what we're doing. Any questions on what we're doing? Is it making sense? Okay, so now if you want to understand what's actually going on here, let's think what happens if the label, the brand of a particular sample is a Ford. In the case of a Ford, what happens is we get 1, 0, 0. So this turns into a 1, this turns into a 0, this turns into a 0. Because those are zeros, the effect of beta 2 and beta 4 vanishes, right? Just multiplying them by 0. And then this just reduces to beta 2. So for any Ford samples, the model is effectively this. Similarly, for any Honda samples, these go away, and this one just turns into beta 3. So we get this model. And finally, for any BMW samples, we get this model. So what you can see that's actually happening is when you apply one-hot coding in this way, you actually are using a different intercept for each category. For the Ford, samples, the intercept is beta 0 plus beta 2. For Honda, it's beta 0 plus beta 3. And for BMW, it's beta 0 plus beta 4. Okay, so that's the effect of one-hot coding, at least when you apply it this way. So remember, we have, if we just think like simple linear regression, we have a line with some slope according to beta 1. Now we're actually going to have 3 different lines. One of those lines is for the Ford samples, one for the Honda, one for the BMW. They will all have the same slope, but they will have different shifts. That's what we've done. Okay. This is a modeling option. As we'll see, it's not the only thing we can do, but it is an option to us. If we encounter categorical data, we can handle it this way. Okay, any questions on what we've done here? Okay. Let's think about another way to do things. So the kind of one-hot coding that we did on the last page led to category-dependent intercepts. What if we know something about our data that tells us that we instead want category-dependent slopes? So let me give you an example why. So using this mile per gallon prediction, given horsepower and brand, where the brands, again, are Ford, Honda, BMW, what if we know that each of these brands actually uses a different way of computing the horsepower? And so when Ford says it's this horsepower, that actually means something different than Honda saying it's this horsepower. So now we know that, the horsepower is actually what we should use a different model for horsepower for the 3 brands. In other words, the slope of the line should be different, not the intercept. So we can do this as well. Once again, we can make these one-hot vectors just like before, but the difference is now we can apply them in a different way. So what's going to happen is we're going to multiply them against the X1 feature. So whenever I have a Ford sample, that means this guy goes to 1, this stuff goes away, and I get this. Whenever I have a Honda sample, these guys go away, this one goes to beta 2x1, and I get this. And similarly for a BMW sample, we get this. So now when you look at these, you can see that they all have the same intercept, beta naught, but they all have different slope terms, beta 1, 2, and 3. So this is another option to us. So it's just always good to be aware of your options and the different kinds of things you can do when you encounter a data set, because maybe that data set deserves one treatment or another. Okay, so in this case, one-hot coding allows a different slope for each category. So one-hot coding is this sort of general concept here that can be applied in different ways. All right. Any questions on this page? Making sense? Okay. So now we do sometimes have to worry a little bit about invertibility issues. So let me show you one case where this happens. When we one-hot code the intercept, which was 2 pages back, it turns out that you can make this matrix A transpose A, this is the thing we want to invert, you can actually make it non-invertible. And that's bad because then you can't invert it. Let's see why this happens. So again, our model in the case of one-hot coding the slope looked like this. And so our beta vector now has 5 entries. And when you think about the rows of our A matrix, they have one of 3 forms. They look either like this, or like this. So the first coefficient in a row of the A matrix is always going to be a 1. The second coefficient in this case is always going to be the feature vector x1, which was horsepower. And then the last 3 terms will come from the one-hot coding. So they'll either be 1, 0, 0, 0, 1, 0, or 0, 0, 1. So all the rows of A will look like this, this, or this. So now, imagine that I made a beta vector that looked like this. If I multiply this beta vector times any of these rows, I will get 0. Because what's going to happen is this 0 is going to cancel out the effect of the feature. The minus 1 will multiply the 1 to give me minus 1. This one will multiply, and then these will multiply either 1, 1, or 1 to give me a 1 in any case. And that 1 from this will cancel out the minus 1 here to give me 0. This will happen for every row in the matrix. So what we're saying is there exists a beta vector, a non-zero beta vector, such that A times beta equals 0. And if A times beta equals 0, then I can multiply this on the left by A transpose, and that must also equal 0. And now, essentially, if I have a matrix, in this case A transpose A, and I found a non-zero vector that I can multiply with that returns a 0-valued result, it means that I have a matrix that's non-invertible or singular. Intuitively, the information about the length of the beta vector is lost once you multiply it by this matrix. There's no way to get it back from what the output of that matrix multiplication gives you. So therefore, you can't invert the system. So this is the issue. This is kind of a short proof that the resulting matrix, when you do this, the resulting matrix will be singular. We won't be able to invert it. We can't compute our least squares solution in an easy way. So there is a way of circumventing this problem, and it's to use a slightly simpler one-hot coding, where you only use the first two, and then the third guy is 0, 0, 0. And let me show you the effect of this. What's going to happen is, essentially, you're not going to have the beta 4 term. So the beta 4 term is going to go away. Everything else will be the same. And it kind of makes sense because you can see that there's a redundancy in this model. There's always 2 terms you're adding to get the intercept. So it's like there's more than you need. So by getting rid of this beta 4, now beta 0 will determine the intercept for the BMWs. Whatever beta 0 is plus beta 3 will give the intercept for Honda, and whatever beta 0 is plus beta 2 will give the intercept for Ford. There's no more redundancy. So this will also cure this invertibility problem. So this is one approach to get around this little problem that we see. There's another approach where you let the matrix be non-invertible, and you use something called regularization, which we'll talk about in Unit 4, but we don't know that tool yet. So, so for now, if you wanted to implement this, I would suggest to do this. Okay. So that's really all I wanted to say about one-hot coding. Are there any questions? Yeah.
How does the non-redundant one-hot coding scheme fix that problem?
How does the one-hot how does this fix the problem? So it fixes it because it gets rid of this last term here. And so what happens is, you see how I was relying on 1 times 1 canceling the minus 1 times 1 here to give 0. What happens is when this 1 turns into a 0, it won't cancel it. So I won't have an entire zeros vector. I'll have something that's not a non-zero vector. And I will no longer say there exists a non-zero beta vector that makes this matrix multiply goes to 0. I can't do that anymore. And I won't have any invertibility problems caused by one-hot coding. Okay.
So does this affect our result? Maybe will it affect our R square if we use 3 variables or 2 variables to represent the brand?
So the problem is that if the matrix is non-invertible, what that means is that there's going to be actually an infinite number of possible beta solutions that will give you the same thing. So on the training data, they will give you all the same performance, but on test data, they will give you very different performance. So that's kind of the issue.
Because then why would we go with the 3 variables at first place? We could have gone with 2 variables.
It's simpler to explain.
Okay.
And if we want to do the slope coding, we need 3. Yeah. So it's just how I decided to explain it. But yeah, it's a good point. In some cases, you don't need it. If you see the redundancy in your model, you should usually take it out. So sometimes you have it, sometimes you don't. It depends on how you apply the one-hot coding. It's a great question. Okay, great. So any other questions about one-hot coding? Okay, so let's move on a little bit. We talked about this a little bit in the last unit, that one of the ways that we can pre-process our data to make linear regression more powerful is to take a feature and square it or cube it or do some nonlinear transformation to the feature. So one interesting thing we can do is, let's say that I have a single variable, x, and I want to do polynomial regression, which means I want to make a model like this. So I'm going to have the beta 0 coefficient, like always, is the intercept. Beta 1, like before, is a slope. But then beta 2 is multiplying x squared, so it's like a quadratic. And then beta 3 is like a cubic, and so on, all the way up to some point where we decide to stop. Beta d is multiplying x to the dth power. So with this model, you can see that we can get a lot more interesting shapes than linear. So for example, in this case, the red is a 3rd order polynomial, the blue is a 5th order polynomial, and the green is a 9th order polynomial. And for the particular data that's shown here with those dots, it looks like the 9th order one is the best fit, at least among these 3. So as you can see, this is a much more sophisticated model than just simple linear regression. The point is that even though it looks really fancy, when you look at these pictures and so on, actually, this is easy to handle using multiple linear regression. All we have to do is define x sub j, which is the jth feature in multiple linear regression, as x to the power j. And then we can just directly apply what we learned in this unit. So in other words, this is our x sub 1, this is our x sub 2, all the way to x sub d. Right? So I've kind of taken this simple in the sense of single variable x nonlinear model, and I've written it as a new model which is linear in all the different betas, but nonlinear in the x's. What's essential for linear regression is that it's linear in the betas. It doesn't need to be linear in the x's. It needs to be linear in the betas. So that's a very powerful thing. And this is just one example of something we could do. Another example is this. What if I take cosine of some frequency omega j times x, where I have different frequencies that gives me different features xj? This is something else we could do. There's a lot of things like this you could imagine doing once you think about it. And you'll have a homework problem to play with this idea here. So this is an instance of feature transformation like we talked about before, a very powerful technique. And it's just one instance of many. But it actually raises a really interesting question. When do you stop? When do you because we started with a single variable x, and we decided to make this expanded into many variables. How do we know what is the highest order we should use? This is actually something called model selection, which is an important topic, and that's the topic of the next unit. So this is really just kind of setting up the problem for the next unit and pointing out that with multiple linear regression, you can do all sorts of interesting things. Okay. Any questions on on this idea, feature transformation idea? Okay. I'll be brief on this slide. This is something you'll actually see in one of the homework problems, and you may have seen it in some of your other coursework. But sometimes when you want to model a system, or let's say a waveform, in this case we have a discrete time waveform where you have t denotes time, and this model, this is called an autoregressive moving average model, or ARMA model. This is what we call a linear time invariant system. It says that the output of the system at time t is some linear combination of the output of the system at previous times plus some linear combination of the inputs at the current and past times. So this is a kind of a powerful general model. You can use it to model tons of stuff. If you know about transfer functions, this is the z-transform of this. If you don't know about them, no problem at all. But here the goal is, in such a system, if we want to apply this model to our data, we have to figure out what these coefficients, the a's and the b's, are. And so the point here is that we can do this with multiple linear regression. We can stack all the unknowns, all the a's and the b's, into our beta vector. And then what we need to do is figure out how to write this y equals, or y approximately equals to a times beta. How do we turn this into that A matrix? So if you think about it, the key point is that the A matrix needs to contain known quantities, right? That is where you put all the stuff you know, all your data. The beta vector must contain unknown quantities that you are trying to fit. And then, of course, y must also be known quantities. Any way that you can do that, once you set up the y, a, and the beta that way, you can apply linear regression. So in this particular case, what you would actually do is, if let's say we look at the very first row of this system. So you have a single y and you have a bunch of elements in the top row of A. You would have something like one of these y's on the left. And then as you go down the different columns of A, you would see yt minus 1, yt minus 2, so on to yt minus m. And then you would have ut minus 1, and so on to finish this out. And that would match how this beta vector was constructed. So just because some of these things are called y doesn't mean you can't put them in the A matrix. If they're known, you can put them in the A matrix. The key is to keep the knowns in the A and the y and the unknowns in the beta. Once you have that, you can apply our linear regression approach and you can solve for the betas. So like I said, you'll get some more practice on the homework. But this has tons of applications. For example, you could learn the dynamics of mechanical systems. You can model the responses of biological systems like neural systems. You can use this for speech coding. You can use this for predicting the stock market. You can use this very widely, this ARMA model. And the point here is that linear regression is all you need to solve the coefficient fitting problem. Okay. All right, so that's it for this unit. Are there any other questions on linear regression? All right, so let me